Welcome back, everybody. So we got an interesting project. This is actually kind of one segment of a job that I've been working on for a couple of months. One of my customers has got this 1960s vintage lathe built in Japan. It's an Ikagi. I've seen them before, but I don't think I ever worked on one. I don't think there's that many of them here. But anyways, it's kind of a long, sad story. They bought it, built a new shop. They restore classic European vehicles, so they don't really have a machine shop or haven't in the past. So when they built their new building, they put in a machine shop section, bought some machine tools, and hired a electrician to wire the building and wire in their machines. The electrician wired the building, wired in the machines, and promptly fried the motors on two of their machines. They've got a a Berco Italian-made head resurfacing machine that got the motor fried because they hooked it up to 480 volts when it was wired 240. And then on this lathe, they had wired it in, and then it was tripping or blowing the fuses every time they tried to run it. One of the employees at the business that owned it looked at it and said, well, I think your voltage is wired wrong. And they rewired it, said there it works, and left. And I got called in initially to level it, check out their wiring. So I checked their wiring, it was correct. Got the lathe ready to run, fired it up, and they had only demoed it for about 15 seconds and shut it off. I leave it sitting there running, and in about 3 minutes there's smoke pouring out of this motor. They had cooked it from playing with it on high voltage when it was wired for low voltage, and just done a slip in, slip out trick, like say, fired it up. Maybe they didn't know, maybe they did. I don't know. But at any rate, hadn't tested it long enough to discover that it had shorted windings, and it'd run a little bit until the heat started building up and smoke came out. So the challenge here is, being Japanese, this thing is oddball as all get outs. I mean, compared to our stuff. Metric motor shaft, 7.5 kilowatts, which, we don't rate motors that way. I mean, new stuff maybe does. So I went hunting around, and in my dad's collection, found this 10-horse Lincoln. Now, I'd done some math. This 7.5 kilowatts is pretty darn close to 10 horse. And a matter of fact, this is 7.5 kilowatts at like a 60% duty cycle. It's got 2 ratings on the tag, and continuous duty, they're only rating it to 5.5 kilowatts. So that 10 horse is actually a little bit more power than this is, because it's rated 10 horse continuous duty. So anyways, I had to get that wired in working because it's been sitting around in the shed for years. Wanted to make sure it was actually going to run smooth, not overheat. We didn't need to get any more trouble going. So I took it over there. Now the tricky part is this thing is a 12 lead motor. And I'm not really sure why the Japanese did this, other than that they must have been planning on running this thing on really crappy low amperage service. They had this set up so that you started it in Y, and then could flip the switch on down to the next position, and it reconfigured it to delta once it was up to speed. So my, I'll say, rudimentary understanding of that is that it lowers the amp draw on startup, and then once it's up to speed, you flip her over to delta run for full power output. So I had to go in and reconfigure the relays, because this is just a typical American Y-wound motor with 9 leads. So I had to go in there and reconfigure the relays. Actually, there's 4 relays in the panel for running this one, and I eliminated 2 of them from the system, because you only need 2 relays to just run a normal 9-wire, because I'm only pulling out the 3 leads. I've got it wired for high voltage, and all the relays are doing is just swapping a couple of the leads for forward and reverse. So I've done that, proved that it spins good. So what we're back here at the shop to do now is, this is the pulley. Aluminum pulley. This is what the Japanese had on this thing, which is beautiful. It works great. They did kind of a strange fitting. This is kind of what I wanted to show you. So this is nuts. The way that this thing was retained is, it's got a plate that went on the end with a couple of bolts in it. You got a couple of bolts here. Well, that's not one of them, but the other one's in here. Anyway, a couple bolts that held that on the end, and then this key, as far as I can tell from looking at it, is hand fitted. It's got a threaded hole in the end of it so that they could pull it back out. And then I initially thought, well, maybe it was a tapered key, because I've seen that before, but as far as I can tell, it's not. It's just somebody hand filed this thing to be a perfectly snug fit in there. Like, it's no slop, just taps in there. It's slightly tapered, but I think that's not so much intentional as it is. I mean, maybe, but it's mostly just a byproduct of hand fitting, right? So anyway, that's how they were dealing with the fact that, you know, there's no taper lock type system like a classic American motor drive would have on it. So I'm going to go ahead. There's about a 3 millimeter difference between this shaft size and this shaft size. So I'm going to bore this out to fit the Lincoln shaft, and then what I've concluded is that it's only going to shallow the keyway up by 1.5 millimeters. I'm going to cut this key down, and this, by the way, is a 10 millimeter wide key. That's a 5/16, which is about 8 millimeter. So I'm going to cut this key down, make it a T-shaped key that fits that keyway and this keyway, and shorten it up enough to deal with the fact that the bore got bigger and therefore the keyway got shallower. So that's what we're about to do. Close enough to get a measurement. Like 261. Yeah, 32 millimeters. So we got a good 100 thou to take out of here anyway. Take a buzz through there and see how that looks running. Says that should slip on there, actually with a little bit of play. I think what I'm going to do, I don't love the retention system. I think I'm actually going to put a little sleeve retainer on this thing when I put it together. And that's something I do pretty frequently with this kind of stuff, because there's no downside to it. When you want it loose, you just put a little heat on it. Let's see here. My expectation is this will slip right on. Well, with the exception maybe some of the boogers and burrs that are in here. Yeah, I gotta clean the burrs up, but she's trying anyways. Alright, so I cleaned it up a bit and it was just what I thought. There were a few like burrs and high spots, just stuff in there that was interfering with it sliding on. It's actually basically I can just barely feel a little movement in it, but a slip fit. So that's just great. And then you can see now the difference in the keyway width. So I got to take this key and carve it up. It's a little tricky because it's got this drilled and tapped hole in it. I halfway thought about starting over with a whole new hunk of key stock, but we're going to go get this in the mill and start carving it into a T-shaped key to fit that thing. Alright. Hit the oil pump. I already put some oil in the cups on the head. I'll reiterate the same thing I beat on every time. It's not possible to over-oil a Bridgeport. I want to see puddles on the floor around your machine if I ever come into your shops to work on your mill. The only exception to that would be if you have the newer style sealed spindle bearings, I have seen one side effect. So if you keep dumping oil in the oil cup, it pools up in the end of the quill, and had people complaining about their quill starts to get hot. And it's because you've got all that oil in there getting churned around in a circle. I'm not sure, to be perfectly honest, when Bridgeport switched. If you've got an older Bridgeport and you haven't replaced them with the newer style, it's safe to say they're not. When I say older, anything from the, I'm going to say 90s back. But even the ones with seals in them, after they've run for a few years, the seals start getting a little wore out, and then they let the oil on through anyway. So, perfect. So I got to show you guys this thing. So these are some of my favorite parallels. I've got a whole set of these. A friend of mine gave these to me. They were something that some old machinist made. I think I've mentioned before, a lot of apprentices this kind of project do. I have a complete set of these. I think they go in 1/16 of an inch, from 1/4 inch up to like 2.5 inches. Extra wide. And I'm sure this guy machined these. These are hardened, precision ground, and there's matched sets of, I've got, of course, pairs of 2 of them. Now, they're so thick that this instance, I'm just using it. It happens to be just a little bit wider than the key itself that I'm working on. So, but that said, man, those old machinists, they did some phenomenal work. I would way rather have some real craftsman's handmade tools like that than the new Chinese junk they're importing now. So I kind of hoard up those old handmade tools when I find them like that. Alright, well, we're going to buzz this thing down a bit and then flip it over. So what I'm trying not to do is break into that threaded hole in the middle. So I've got to thin the key down, and I want to do it by shaving down each side a little bit at a time. And try not to break into those threads at all. So another thing, guys, if you want your drawbars and your collets to last, put some oil in these things. Can't tell you how many shops will replace some drawbars in left and right for no good reason, because they insist on running them dry and just tearing up the threads on their drawbar. Matter of fact, something else I'm going to do right now while I'm lecturing all you is pull the drawbar up, put a drop of oil there where the drawbar meets the top of the spindle too, otherwise you wear the top of your spindle out over time. Alright. So, ball screws, like I mentioned before, I have to make sure that I've either got my hand on the lever or got the lock set, because it will take it and run with it if you don't. I guess I want to leave the, get my axes mixed up here. I locked the X and left the Y loose. That would have been counterproductive. Alright, we're going to take, say, 20 thou and take a buzz across there. Matter of fact, I want to give her a little spritz of something. Take it back here. This is just a high-speed tool steel cutter. I use a lot of, like, this is just cheap penetrating oil is all this is. Just a little bit of something on there to help keep the cutter, help it live a little longer. Oh yeah, very soft key stock. So. Yes, I've got power feed, but I don't use it all that much. I like to be able to feel my tooling. If I'm making multiple cuts that are the same, then I'll start setting it up. But most of the time, if it's just a cut here, cut there, I just go ahead and Alright, so I have got 24 thousandths to remove here. So I'm going to flip this thing over. buzz the other side. I'm glad we stopped when we did, because that gives me almost even material removal off both sides. And mind you, I don't especially care like that it comes off one side or the other. I'm just trying to keep as much material on each side of that threaded hole as I possibly can. And this time I care a little bit more about being flat, so we're going to tap in. Now what you saw there, I don't know if you noticed that I hit it and then that was loose. I hit it too hard and it bounced back up. You got to find that magic amount of force to get it to drop to the bottom, but without recoiling. So I don't know if you could see that bits of linty looking junk that went flying through the air about the time that I was vacuuming up that last batch of chips, but that's got its own funny little story connected to it. So if you watch the video, I don't know, a couple back, you know that I just got a plasma cutter and then it had a mouse nest in it. So what I didn't show in that was off camera, I had dug more of the mouse nest out and it wasn't as clean as I wanted, so I thought to myself, you know, I'll just vacuum that out. Now I just told you, I took the filter out of this vacuum because you don't need it sucking up metal chips, makes it more powerful, all of that stuff. Well, guess what? You do need one when you suck up a mouse nest. It made a good comedy video, that's all I got to say. That thing, I mean, I blew a lint ball of just, you know, mouse pea smelling disgustingness all over that end of the shop. I mean, it's 10 minutes for all them fine little particles to land again, and huge sweeping project. So just remember, you pull the filter out, don't try sucking something like that up. It was pretty dumb. Hey, Wiggles.
Maybe have a waffle.
Sure, have a waffle.
Where's the toaster?
We just have that kind of toaster, the toaster oven. You want to? So that's 161 thousandths deep. I want to go to 165, I think, just to be on the safe side. There is 100. This could be its own new problem here. We gotta get some safety devices in here. I do not want to mill my lathe jaws. All the marks that are on these came on this when I got it. So you're gonna be darn close. So I am like right there, guys. I'm at 162. I wanted to be at 165. Oh man. I'll come give you a hand in a minute. So, as I was saying, like, we are just skimming the lathe, or that lathe jaw, the jaw of that vise here. It is so close, it's terrifying. Looks good though. So. Minus 0.3155. So we got 79 thousandths. So divide that by 2 gives me 39 and a half. So 0.0395 is how far I need to cut in on each side to make this key the width that I want it to be. So we're going to come up here, come up and kiss the side of this thing. Y0. Come in 0.395. Buzz my way down the side of her. Move my paper so it won't destroy it. I am climb milling, by the way. You probably noticed that. Ooh, don't like that, guys. I'm touching the lathe jaw. I hear the noise that it's making. I don't know why. It could be that the end mill sucked out a little. It could be that or not lathe jaw, but the vice jaw. It could be that the vice jaw itself is not very accurate, but not worth risking it. So I drop down a little bit. If my key doesn't fit quite right, we'll come back and do a little bit of hand fitting with a file or something. Not interested in putting a groove in my vice jaw and or crashing my end mill. Over to the other side. I'm climb milling, and that's because it's better for the cutter. I've mentioned that in other videos, but this first time, so I can't even remember which one of my many machining books I've got. I'll take you for a walk through and show you my library a minute again. But I have a lot of books. I do a lot of reading, and I think it was the McGraw-Hill Machining Handbook from like 1985. They discuss it in great detail that if you're plow milling, you're starting from a thin shave of nothing and the chip gets thicker. Climb milling, you're biting into the metal at the thickest point of the chip, going to zero. So the effect of plow milling is that you're basically rubbing for a few fractions of a second before it starts to cut. Reduces tool life substantially. So, but you can't get away with climb milling with an Acme screw machine without seriously risking damage. So I'm not telling you all ought to go take your Bridgeport and start climb milling. I don't want to be responsible for the wrecked tooling. So anyway, the reason I can get away with climb milling is I have ball screws. You need a zero backlash screw. If you're going to try climb milling with a Bridgeport with Acme screws, the only way I know of to safely do it is to slightly apply your table locks, but obviously, you're putting more wear on your gibs by doing that. I really don't love seeing people do that. But if you absolutely have got to, then that's the only way I know of to safely accomplish it. 0.315. 0.315. I believe we have got a winner, folks. All right. Look at this, guys. We have got, like, perfect tap fit as far as the width goes. Now the only question that remains to be answered is, did we get the heights all worked out right? I'm going to go ahead and, if I can get it back out of there after just smacking it like that. Go ahead and clean this key slot up a little bit, and then tap this in and then see if the pulley will slide on. I'll bring you back when we get to that stage. All right, so I got down there. It's pretty snug fit. I had to tap it on all the way, and you can see I did make a flat spot right here. That's the problem with driving on something that's soft. I should have grabbed wood. You know, I had an aluminum driver, but it's an aluminum piece, so it mushroomed out the edge a little bit. But the fit was fantastic, though. It's nothing crazy. You'll pull it right back off with a puller, but basically no slop. By the time, like, that key is so perfectly fitted to its opening that we got a zero clearance fit on everything. So I'm very happy with that. What I need to do now is, I guess I didn't point that out earlier, the way this was all returned, maybe I did, they've drilled and tapped the end of this shaft and they had this plate. That's what kept this one together. So this one, I'm not going to try drilling and tapping 2 holes. I'm going to drill and tap one right in the center.
Daddy, this
For about a 5/16, and then I'll make a cap plate that goes on it, because on this one, this shaft is a little shorter, so there was some clearance between the face of the pulley and the end of the shaft. This was actually tightening up against that shoulder. This one, shaft's a little longer, so it's sticking out, so I'm going to have to make a custom cap that reaches over the end of the shaft. But anyhow, so I'm going to set up, drill and tap the end of this, just probably freehand that. Thought about trying to put it in the drill press, but for what it does, I think I'll just go ahead and freehand drill it, tap it, and put in a screw. All right, got our hole drilled and tapped. I just freehanded all of that. You can do a pretty good job on something like this. Already got a center drilled in it, and where you're standing, I've got this motor stood on end. So anyway, now I've got to go make my end cap. I'll shoot a little video of that process. Okay. There. Get my loose sleeves rolled up here. I don't need to get sucked into the lathe because some loose clothing gets snagged here. Alright, so I got this sliced off in the lathe. That came out perfect. I cut the very bottom of my hole that I had drilled in here. So now this is where it's a little tricky, is getting squared, trued up in here. All you can do is play with it, see how it spins, play with it some more, see how it spins. So that's pretty good. Not perfect, but pretty good. I'm looking at the inside face, looking for wobble in that. Tapping on it here without it real tight in the jaws, trying to let it. And that's so close, we're going to run it. Alright, so snuggle up a little more, not too tight just because I don't want a bunch of big ugly marks in my part. And we'll face this sucker off. There we have it. One nice, stout little retainer washer, I guess I'd call it. Let's go put this thing together. All right, time for the first test fit here. Yeah, that's what I was hoping for. We got just a little side play there. Now, did we get all of our... Oh yeah, we're threaded deep enough. Sorry about that. Here we are. All right, there's Wiggles driving the tractor. All right, well, folks, I'd call that a win. We are ready to go to work here. This thing's assembled. I'll lay it down here a minute. So there you have it. Pulley used to be on that one, is now outfitted and ready to rock and roll on this. So next week we will hopefully have this Ikagi up and running. I'll try and shoot some video of it in operation. So till next time, have a good one.